All right, let's take a deep dive into this paper.
Okay.
Towards the quantitative verification of deep learning for safe perception.
Right.
It's tackling a really important issue.
Yeah.
How do we verify the safety of deep learning, especially in something as critical as automated driving?
Yeah, definitely.
We're all aware of deep learning's strengths in perception tasks, but that black box problem makes it tough to truly guarantee safety, right?
Absolutely. And this paper presents a really interesting approach.
Okay.
It focuses on quantifying the safety of these systems,
Okay.
which is a huge step towards building trust in them.
Okay, so let's get into it.
Sure.
They start by breaking down uncertainty, which seems like a natural starting point when you're talking about safety and deep learning.
Right. They lay out those 3 types of uncertainty:
Yeah.
aleatoric, epistemic, and ontological, and how they impact every stage of the automated driving process, from sensing the environment all the way to acting on that information.
Let's take an example to make this more concrete.
Okay.
Say our self-driving car is approaching an intersection.
Sure.
How might these uncertainties come into play?
Good point. Aleatoric uncertainty is always there. It's the inherent randomness,
Okay.
maybe some sensor noise or slight variations in how the car's cameras perceive the world. We can model this statistically,
Right.
but we can't eliminate it.
Okay.
Then there's epistemic uncertainty. This comes from limitations in our knowledge or models.
Right.
For example, our perception system might have difficulty accurately detecting a partially obscured pedestrian, especially if it hasn't encountered many similar situations during training.
And that brings us to ontological uncertainty. Those
Yeah.
unknown unknowns. That's the trickiest one.
Definitely. It's the stuff we don't even know we need to worry about.
Right.
Imagine a sudden, unexpected event like a child chasing a ball into the street from behind a parked car.
Oh, wow.
Our current perception systems might not even be designed to recognize and react to such a scenario.
And this is where deep learning gets even more interesting and challenging.
Exactly. Deep learning can actually help us turn some of the epistemic uncertainty into a more quantifiable aleatoric form. But at the same time, it can also introduce new forms of uncertainty due to its black box nature.
So how does the paper propose to address this?
Well,
It seems like breaking down the problem is a key part of their approach.
that's right. They introduce this idea of decomposing risk,
Okay.
starting from the overall system level and then breaking it down into specific performance targets for each deep learning component.
I see.
Yeah.
So instead of saying this entire perception system needs to be 99% accurate,
Right.
you're saying
Yeah.
this object detection module needs to be 99.5% accurate within this specific set of conditions. And this lane keeping module needs to be 99.8% accurate under these other conditions and so on.
Precisely.
Okay.
And to do this effectively, they introduced the concept of micro-operational design domains, or ODD.
From what I understand, ODDs are essentially subdivisions of the overall operational design domain, ODD, that are specifically tailored to deep learning performance.
Yeah.
Can you elaborate on that?
Sure. Think about the ODD as the general operating environment of the vehicle, all the different situations it might encounter.
Okay.
ODDs take this a step further and break down the ODD into smaller chunks
Got it.
based on factors that could systematically affect deep learning performance.
So instead of assuming that the system will perform equally well in all conditions,
Right.
we acknowledge that certain factors like heavy rain or nighttime driving
Yeah.
might pose unique challenges for these deep learning components.
Exactly. It's about moving away from broad assumptions to more precise and realistic assessments.
I'm starting to see how this all connects.
Good.
But how do they actually link these ODDs to the performance of the deep learning components?
Well,
How do they determine what level of accuracy is needed in each ODD?
the paper takes us on a journey, following the flow of information within a typical automated driving perception architecture.
Okay.
And you can actually refer to Figure 2 in the paper for a visual representation of this.
Okay, so we're talking about how the system takes in data from all those sensors,
Uh-huh.
processes it,
Yeah.
and then uses that information to understand the environment and make driving decisions.
Right. And this is where those different types of redundancy come in.
Oh.
Safety envelopes for the deep learning modules, time-based redundancy,
Right.
plausibility checks,
Yeah.
and of course sensor fusion.
These redundancies play a crucial role in increasing the system's reliability.
Right.
For example, sensor fusion might combine data from cameras, LiDAR, and radar
Exactly.
to more reliably detect objects, especially in challenging conditions.
Exactly. The paper delves into how the performance of each component within its designated ODD,
Okay.
in conjunction with these redundancies, contributes to the overall performance of the perception system. They even factor in the dependencies between different information sources.
So it's not just about each component hitting a certain accuracy target in isolation.
Right.
It's about how they all work together,
Uh-huh.
potentially compensating for each other's weaknesses
Yeah.
to achieve that overall system-level safety goal.
Right, and that's a crucial insight
Okay.
because it allows us to move towards a more comprehensive and realistic evaluation of these complex systems.
Right. This is all making a lot more sense now.
Good.
But we've only just begun to scratch the surface of this paper.
Indeed, we still need to talk about how they propose to actually test these systems, how they connect this framework to existing safety standards, and what challenges they see for future research.
Sounds like we have a lot more ground to cover. Let's pick right back up in part 2.
Great. Picking up where we left off, let's delve into how the paper tackles the challenge of testing these deep learning components within their specific micro ODDs.
Okay, so
Yeah.
it seems like a daunting task, given the sheer number of potential scenarios a self-driving car might encounter. How do you even begin to approach testing in a way that's both comprehensive and efficient?
Well, the paper advocates for a risk-based approach, which makes a lot of sense in this context.
Okay.
Instead of trying to test everything equally, they suggest focusing testing efforts on the situations that carry the highest risk.
So we're talking about prioritizing those scenarios where the potential consequences of failure are most severe and the likelihood of encountering those situations is relatively high.
Precisely, this approach allows for more targeted and efficient testing
Okay.
by allocating resources where they matter most.
I see how micro-ODDs play a crucial role here. You'd want to test more rigorously in a micro-ODD that represents dense urban traffic with lots of pedestrians,
Right.
compared to, say, a micro-ODD representing highway driving with fewer complex interactions.
Exactly. And the authors emphasize that both the performance targets and the intensity of testing should be tailored to the specific risk profile of each micro ODD.
This idea of connecting risk assessment to testing intensity is really intriguing. But how do they actually propose to measure the performance of these deep learning components within each micro-ODD?
Well, they delve into various qualitative and quantitative methods for evaluating uncertainty in deep learning models, and they emphasize the importance of empirical soundness,
Right.
making sure that your measurements truly reflect real-world behavior.
Right, because having good numbers in a controlled lab setting doesn't necessarily guarantee that the system will perform equally well out on the open road.
Absolutely. So they start by emphasizing the foundational aspect of data management.
Okay.
If the training data is flawed, biased, or incomplete, the model will inherit those weaknesses.
It's like building a house on a shaky foundation.
Right.
You can have the best blueprints and the most skilled builders, but if the foundation is compromised, the whole structure is at risk.
That's a great analogy. So they talk about ensuring data suitability coverage and quality coincidence. The training data needs to be relevant to the task at hand, representative of the real-world scenarios the system will encounter, and free from errors or inconsistencies.
That makes sense, but once you have good data, you need to make sure the model is actually learning from it effectively.
Right, and that's where model learning comes in.
Okay.
They highlight techniques like robust learning, which aims to make the model less sensitive to noise or variations in the data.
So if the model encounters a slightly blurry image or an object that's partially obscured, it can still make a reliable prediction.
Exactly. They also talk about the importance of training specification being very clear and deliberate about what you want the model to learn and how you're measuring its success.
Because you don't want the model to learn unintended patterns or optimize for the wrong things.
Precisely. And once the model is trained,
Okay.
we move on to validation, making sure it performs well on unseen data.
That's where techniques like out-of-distribution testing come in, right?
Right.
Seeing how well the model generalizes to situations that are outside of its training data.
You want to know how the model will react when it encounters something unexpected? They also discuss sensitivity analysis, essentially probing the model to see how its output changes when you tweak the input parameters.
So it's like trying to understand the model's decision-making process, even if we can't peer directly inside the black box.
Exactly. But they go even further and talk about model verification,
Okay.
which takes a step back and independently checks that the model is doing what it's supposed to do.
So it's like having a third-party auditor come in and make sure everything is up to code.
That's a good way to put it. They specifically mention formal verification,
Right.
which uses mathematical methods to prove certain properties about the model's behavior. It's a very rigorous approach, but it's still an active area of research.
It sounds incredibly complex, but the potential benefits are huge if it can give us those mathematical guarantees of safety.
Absolutely. And alongside those qualitative methods, they also delve into specific quantitative metrics for evaluating these models.
We're talking about going beyond just basic measures of accuracy, right?
Mm.
Getting a more nuanced and holistic understanding of how these models perform.
Exactly. They talk about metrics that specifically target issues like generalizability, robustness, explainability, and even fairness.
Let's unpack those a bit, because those seem really important, especially in the context of self-driving cars.
Sure. When we talk about generalization, we're interested in how well the model performs on new unseen data. One metric they mention is scenario coverage, which assesses how well the training data represents the range of scenarios the model might encounter.
The wider the coverage, the more confident we can be that the model won't be completely thrown off by a new or unexpected situation.
What about robustness? How do they propose to measure that?
Robustness is all about how sensitive the model is to variations or noise in the data. One metric they highlight is the mean performance under corruption.
Essentially, you test the model on data sets that have been intentionally corrupted, like adding noise to images or blurring them. It's a way to see how well the model handles those imperfections that are inevitable in the real world.
It's like a stress test for the model's perception. If it can handle those corrupted inputs and still make accurate predictions, that's a good sign.
Exactly. And then there are metrics that focus specifically on adversarial attacks, where someone is intentionally trying to fool the model.
Right.
They mention adversarial confidence loss, which measures how easily an attacker can trick the model and reduce its confidence in its predictions.
So that got metrics for generalization and robustness. What about explainability? That's a big one, especially when we're talking about safety-critical systems.
Yeah, it is, and it's a particularly tricky one because deep learning models are notoriously opaque, but researchers are working on developing metrics that can shed some light on how these models arrive at their decisions.
So instead of just having a black box that spits out an answer, we want to understand the why behind that answer.
Precisely, one approach they mention is using heat map techniques, which can visualize which parts of the input data the model is paying the most attention to.
Okay.
This can give us some clues about its decision-making process.
So we can see, for example, if the model is focusing on the right features when deciding whether to brake for a pedestrian.
Yeah.
What about fairness? How do they approach that?
Fairness is about making sure that the model isn't making biased or discriminatory decisions in the context of self-driving cars. This might mean ensuring that the model doesn't have a higher error rate when detecting pedestrians with certain characteristics.
That's a critical point. We don't want these systems to perpetuate or amplify existing societal biases.
Absolutely. And while there's no easy solution, the authors point to metrics that can be used to quantify bias in the model's predictions. And then once those biases are identified, there are techniques like data augmentation or adjusting the model's training process that can be used to try to mitigate those biases.
It's a complex issue, but it's encouraging to see that researchers are actively working on developing metrics and techniques to address it.
Absolutely. And this paper gives us a great overview of the current state of the art in terms of both qualitative and quantitative methods for evaluating these systems.
We've covered so much ground in this part, from risk-based testing strategies to the importance of data management and all those fascinating metrics for evaluating these complex models.
But there's still more to come. The authors don't shy away from acknowledging the remaining challenges and outlining areas for future research.
So let's dive into those in the final part of our deep dive.
Okay.
So we've explored the paper's framework for quantifying the safety of deep learning in automated driving, from breaking down risk and defining micro-ODDs to the nitty-gritty of testing and evaluation.
But as with any groundbreaking research, this paper doesn't just provide answers, it opens up a whole new set of questions and challenges.
Right. The authors are very clear about the areas where more research is needed. What stood out to you as the most pressing issues?
Well, the big one that always looms over us in this field is ontological uncertainty, those unknown unknowns that we can't anticipate or test for directly.
It's that nagging feeling that no matter how thorough we are, there might be something out there that could completely blindside our systems.
Exactly. And the paper rightly emphasizes that we need to develop methods that specifically target and mitigate ontological uncertainty. It's not enough to just hope we've covered everything we need to be proactive in seeking out potential blind spots.
I'm curious, what might those methods look like? Are we talking about fundamentally new ways of designing and training these systems?
It's an active area of research, but some promising avenues include exploring methods that encourage more diverse and robust representations within the models, techniques that can detect anomalous or out-of-distribution data more effectively, and even incorporating elements of human-like reasoning or common sense into these systems.
That's fascinating stuff. It seems like addressing ontological uncertainty will require us to push the boundaries of what we currently understand about deep learning.
Absolutely. But it's a challenge we have to face head on if we want to build truly trustworthy and reliable AI systems, especially in domains like automated driving where safety is paramount.
The authors also highlight the need for a clearer link between safety integrity levels, SILs, and those test confidence levels we discussed earlier.
Right. It's relatively straightforward to define a system's required SIL based on industry standards like ISO 26262, but translating that SIL into a specific set of testing requirements and acceptable confidence levels for deep learning is still an open question.
So it's about bridging the gap between those high-level safety standards and the practical realities of evaluating these complex deep learning systems.
Exactly. And this is where the interplay between SILs and redundancy gets really interesting.
How so?
Well, think about it. If you have multiple redundant components performing the same safety critical function, do you still need the same level of confidence in each individual component? Or can you relax those requirements a bit, knowing that the system as a whole is more robust?
That's a great question. It seems like finding that right balance between rigor and practicality will be crucial, especially as these systems become more complex.
Absolutely. And the paper touches on the concept of acyl decomposition, which is used in ISO 26262, to break down those high-level automotive safety integrity levels into requirements for individual components. But how exactly that applies to the world of deep learning testing is still an open question.
So it's like we need a new set of guidelines or best practices for applying these existing safety standards to this rapidly evolving field of deep learning.
Right. And on top of all of that, we also need to consider the challenge of scalability as the number of micro ODDs grows as we factor in more and more variables that could affect system performance. We need testing methods that can handle that increasing complexity.
It's a bit overwhelming to think about trying to map out and test for every possible scenario a self-driving car might encounter.
It is, and this is where the paper calls for more research into developing testing methods and metrics that are both rigorous and scalable. We need to find ways to efficiently and reliably evaluate these systems as they become more intricate and operate in more diverse environments.
So it's not just about safety, right? These quantitative approaches could be valuable for evaluating the general reliability of deep learning systems across many different domains.
Absolutely. Imagine being able to quantify the reliability of a deep learning-based medical diagnosis system or a financial trading algorithm. The potential applications are vast.
It's really exciting to think about the possibilities, and this paper lays out a solid foundation for moving forward. I'm curious, what's your biggest takeaway from all of this?
For me, it's the emphasis on moving from qualitative assessments to quantifiable measures of safety and reliability. This shift is essential for building trust in these systems, and this paper provides a roadmap for making that happen.
I agree. This paper has been a real deep dive into the challenges and opportunities at the forefront of AI safety, and I think it's given us a lot to think about. Thanks for joining me on this deep dive.
It's been a pleasure.